In this video, we'll go over how to find the domain of functions. Okay, so I'm going to get into an example. So let's find the domain of the following functions. Okay, so in part A, I got f of x equals square root of 3 minus x. So remember, domain means all of the values I'm allowed to plug in for x. Everything I can plug in. So the way I'm going to think about this is, what are the restrictions? What are the restrictions that I have on my inputs? Is there anything that's kind of limiting the values I'm allowed to plug in? Okay, because if I have a square root, there's one thing I need to make sure happens. Well, that's the thing that's inside the root, 3 minus x. Well, that definitely needs to be greater than or equal to 0. Okay, so this gives me an inequality that I now need to solve. This is a linear inequality. Like this looks like the equation of a line right here. So this is one of those easier ones where I can just isolate the x. Okay, so if I just move the x over, we'll get 3 is greater than or equal to x. In other words, if I write x first, x is less than or equal to 3, and that's my domain. I just got to put it on a number line, an interval notation. So on a number line, I'd plot 3 on it, and because x can be equal to 3, 3 is shaded, and then I want to shade in the values less than 3. So that's all of this. So in interval notation, this would be negative infinity, parentheses, to 3 with a bracket, because 3 is included. Okay. All right, so that is my answer. That is my domain in interval notation. Those are the x values I'm allowed to plug in for x. Okay. All right, let's do B. So B, I got f of x equals 1 over x squared minus 10. And again, I want to find the domain. So I'm going to think about what are the restrictions on our inputs. Okay, so this one, there's a different type of restriction because we don't have a square root. The way that this can be undefined is if the denominator is 0. So my restriction is my denominator, x squared minus 10, that should not be equal to 0. Okay, so let's solve this. So if I were to move the 10 over, I get x squared shouldn't be equal to 10. And if I square root both sides, that means x is not going to be equal to square root of 10, but I need to plus or minus. If I square root both sides, I need to put a plus or minus. So x should not be those numbers, positive or negative root 10. Okay, so if I put this on a number line, I'll put negative root 10 and positive root 10 on my number line. Both of those should be open circles because I don't want x to be those numbers. If x was those numbers, it's making the denominator 0, and that makes my function undefined. Okay, but everything else is good, so I shade in everything else. So I shade in all of this, I shade in the middle, and then I shade in the stuff to the right. All of those other numbers are good. So in interval notation, this would be negative infinity to negative root 10, parentheses, because it's not included, union negative root 10 to positive root 10. Now let me give myself some more room. One more interval, union, parentheses, root 10 to infinity. All right, that is the domain for part B. Okay, let's do some more examples. And as we go through these, I'm slowly going to ramp up the difficulty. Okay, so part C. All right, so I got 1 over absolute value of x minus 10. So again, let's think about, are there any restrictions on my inputs? So far we've seen 2 types of restrictions. If I have a even root, like a square root, like I had in part A, the thing that's inside of it has to be greater than or equal to 0. The other type of restriction that we've seen is, well, if I have a denominator, like x squared minus 10, well, that better not be equal to 0. So which of those restrictions do we have in part C? Well, I got a denominator, so that denominator better not be 0. Absolute value of x minus 10, we don't want it to be equal to 0. And if I move the 10 over, this is saying absolute value of x should not be equal to 10. Ooh, okay, so there's 2 bad numbers that I could plug in to the absolute value to get 10 out. I wouldn't want x to be equal to 10 or negative 10. Plus or minus 10, both of those are going to be bad. If I plug in either one of those into my function, the denominator is 0. Okay, so I go to my number line, and negative 10 and positive 10, I don't want to include them, open circles, but everything else is okay. Everything else is okay, so it's shaded in. So I shade in everything else, shade in everything else. And then I can write an interval notation, negative infinity to negative 10, parentheses, parentheses, union my next interval is from negative 10 to positive 10, and then union my last interval is from parentheses 10 to infinity. That's my domain. That is our domain. Okay, let's look at another example. All right, so what if I changed the sign on the denominator and made it absolute value of x plus 10? So again, I'm going to think about my restrictions. Okay, so anytime I do a domain problem like this, I'm going to start off by explicitly labeling my restrictions. It helps me organize my work a lot. Okay, so, well, again, there's a denominator. So I see one restriction here. And that denominator, absolute value of x plus 10, well, I don't want it to be equal to 0. And if I move that 10 over, I get absolute value of x is not equal to negative 10. So, well, let's think about when that would happen. When is absolute value of x going to be equal to negative 10? Well, this never happens because the absolute value of x is always non-negative. Let me just say, well, absolute value of x can't be negative. So that means all x values are going to work. There's nothing that's going to make that denominator be 0. All right, so everything works. So on my number line, let me put this in a different color. That means everything is going to be shaded. Everything is shaded. Shade in everything. So in interval notation, that would be negative infinity to infinity. Okay, so that is my domain here. So I'm going to box that. Okay, so what seemed like it was a restriction ended up not really mattering because there's no way this denominator was going to be 0. Okay. All right, so part E here. All right, so this is where the difficulty will kind of ramp up, I think. All right, so with this function, I see two restrictions. I see two restrictions here. So what I want you to do at this point is pause the video and see if you can identify what those two restrictions are. Give it a pause for 1 minute. 4, 3, 2, 1. Pause the video. Pause it for 1 minute. See if you can identify those restrictions. All right, so hopefully you did that. Hopefully you paused it and thought about what the restrictions here might be. Okay, so there's a denominator here, x minus 3. So that denominator better not be 0. Well, that's another way of just saying x better not be equal to 3. Okay, so that is one restriction coming from the denominator. But there's also an even root. There's this square root. So if I have an even root, what's inside of it, x minus 10 over x minus 3, that inside needs to be greater than or equal to 0. So notice I'm not saying the whole square root is greater than or equal to 0. It's only what's inside it that needs to be greater than or equal to 0. That is my restriction here. Okay, so I got this inequality now that I need to solve. Ooh, and this is not one of those linear ones, not quadratic. So to solve this, I'm going to need the cut point method. Ooh, okay, so let's make it a comeback. Cut point method. This is one of the reasons why we needed to talk about the cut point method back when we did our inequalities. It's because it was going to show up later in this domain stuff. Okay, so, well, let's do the cut point method. In fact, the first step of cut point method is already done. We already have 0 on one side. And then the left-hand side is already kind of factored for us. So we are ready to say what those cut points are. So the cut points now are going to be, well, what makes this expression be 0 and what makes it undefined? So it's undefined when the denominator is 0. That's when x is 3. And the whole fraction will be 0 if the numerator is 0. And that happens when x is 10. So those are my cut points. All right, so let's take those cut points. Let's put them on let's make a sign chart. So I'll put 3 on the sign chart, or sorry, tick mark at 3, tick mark at 10. And then I am going to put every factor that shows up in my expression. X minus 10 and x minus 3. I separate out some rows here. And then where the tick marks are, the cut points, I'll separate out some columns. And now I want to think about, what's the sign of each factor going to be on each side of these cut points. So remember, there's a couple ways I could do this. Like if I think about something smaller than 3, I could pick a test point, like 2 for example, and I could plug that into x minus 10. And if I did that, I'd get negative 8, and that's a negative value. And I could keep going like that. I could keep picking a test point in each region, and I get signs. But remember, there's a more efficient way. And the more efficient way is to think about, if I look at this factor, what would I plug in for x to make it be 0? Well, I would plug in 10. And then let's think about what happens on either side of 10. So if I plug in anything smaller than 10 into x minus 10, it's going to be negative. So it's going to be negative the whole way, negative here and negative there. But if I plug in anything bigger than 10 into x minus 10, it's going to be positive. So it's going to be positive here. Okay, so nice. So let's use this more efficient way for the bottom factor. So x minus 3, what makes the x minus 3 be 0? Well, it's 3. And if I plug in anything smaller than 3, it's going to be negative the whole way. And if I plug in anything bigger than 3 into x minus 3, it's going to be positive. So nice. So now I just got to put these together and get the sign of the whole thing. Okay. So just as a brief review, this first row is saying, in my inequality, the numerator is negative and the denominator is negative. And if I have a negative divided by negative, that makes a positive. So two negatives like that make a positive. Okay, similarly in this last column, two positives make a positive. But in the middle, one negative, well, that's going to keep the whole thing negative. Okay, so I know where it's positive and negative. Now I'm going to think about what I'm going to shade and where my open and close circles. So in my inequality, I want this expression to be greater than or equal to 0, which means I'm looking for the positive regions. So let's shade in the positive regions. So here's a positive region. Deliberately going to leave some space for the cut point, because I'll think about if it's open or closed. And here's a positive region to shade in. So now let's think about those cut points. So remember that something that makes it undefined, like 3, that's always open. Because if I plug it in, it makes it undefined. There's no way that's going to satisfy the inequality. But the other cut point, x equals 10, the ones that come from the numerator, if I plug that into the inequality, if I plug it into here, the whole fraction becomes 0, and I'll get 0 is greater than or equal to 0. And that's true. That is true. So if it's true, it satisfies the inequality. So 10 should be shaded in. It's satisfying the inequality. Okay. So for restriction 2, I needed the cut point method to handle that. I can't forget about restriction 1. So I still have this restriction 1 here. That's saying x is not equal to 3. Oh, but that's already taken care of on my number line, which is kind of nice. So this first restriction is saying, well, 3 should be open. 3 should be open, but it already was open in our sign chart. Okay, so let's just write this in interval notation. I'll get negative infinity to 3, parentheses, it's not included, union, bracket at 10, it is included, until infinity. Okay, that is my domain. That is our domain. All right, let's do a few more of these. Okay, so part F. So part F, I got, this time, instead of one big square root, I have 2 individual square roots on the top and on the bottom. So let's think about restrictions here. So it turns out this function is different than the last one. Having two square roots separately is different than just having one big square root. Because if I have one big square root, let me write this on the side. If I have one big square root and I have a negative on the top and a negative on the bottom, well, that ends up giving me a positive inside the square root, and that's okay. But like in part F, if I had two individual square roots and I had negatives inside of each of them, well, that would be undefined. That would be undefined. Okay, so part E and part F are actually different because they may have different domains. Okay. All right, so let's think about restrictions for F. So for F, I see three restrictions. I see three restrictions here for part F. Okay, so I want you to pause the video, give it a pause for 2 minutes, see if you can identify all three restrictions. That's the key to doing these. 4, 3, 2, 1, pause it. Pause it for 2 minutes, see if you can get those restrictions. All right, so hopefully you did that. Hopefully you paused it for about 2 minutes to get those restrictions. So let's talk about them. All right, so there's a denominator. There's a denominator. It's that whole square root thing. I got to think about what would make that denominator be 0. That's 3. So x better not be equal to 3. That would make the denominator 0. Okay, and I see two even roots. There's this square root on the top, and there's this square root on the bottom. Okay, so I better make sure what's inside of them is greater than or equal to 0. So the bottom square root, what's inside is x minus 3. That better be greater than or equal to 0. And the square root on the top, that has x minus 10 inside of it. That better be greater than or equal to 0. So these two inequalities that I have, well, these are linear. These are the easy ones. I don't need cut point method. I can just isolate x. So this one gives me x is greater than or equal to 3. The bottom one gives me x is greater than or equal to 10. Okay, so now I got to think about all of these. I got to think about all these together because I need the first thing to happen, and I need x to be greater than or equal to 3. And at the same time, I also need x to be greater than or equal to 10. Okay, so I'm going to handle this kind of bit by bit. If I try to put these first two together, if I think about a number line for that, so I need x to not be equal to 3. That's what the first restriction says. And I need x to be greater than or equal to 3. Well, for both of those to happen, that means I'll put a tick mark at 3. Well, 3 should be open. 3 should be open, and then I'm going to be shading the stuff that's bigger than 3. In other words, those two restrictions combined are basically saying, well, x is bigger than 3. If x is not allowed to be equal to 3, but x needs to be greater than or equal to 3 in restriction 2, that's another way of saying, well, x is just greater than 3. 3 should be open, but everything bigger than 3 is good. Okay, all right, so now let's draw a number line for this last restriction. So for the last restriction, x is greater than or equal to 10, so I'll put 10 on the number line. And 10 is bigger than 3, that's why I'm putting it to the right. And it's a closed circle because there's an equal sign on 10. And then I shade in stuff to the right. Okay, and now, remember, I need this purple number line to happen, and I also need the bottom number line to happen. And we've seen that the word and, taking it back to chapter 1, means an intersection. I got to do an intersection of these two number lines. So and means I got to do an intersection. And an intersection means I draw a number line. I draw a new number line. So I draw a new number line where I am only going to shade in the values that are common to both of them. Okay, so the first number that's common to both, that's shaded in both of them, is 10. 10 is shaded in both. And then everything to the right of 10 is shaded in both. Okay, and that is my domain on a number line. So in interval notation, this would be bracket at 10 onwards to infinity. And that is my domain. Okay, so notice that the domain for part F is different than the domain for part E. Like those two functions look very similar, but they have different domains. They have different domains because of this thing that we observed earlier. If I have one big square root, having two negatives inside makes it okay because they become positive. But with two individual square roots, if I have a negative inside of each of them, well, that's bad. That's going to be undefined. And that's actually why for part F, the domain was smaller. There was less in the domain than there was in part E. Yeah. All right. Okay, so let's look at one more example in this video. So another similar looking one, slightly different, got a slightly more complicated denominator. And let's identify those restrictions. So our restrictions. Okay, and again, for this one, there are three restrictions. So one comes from the fact that there's a denominator. So from the denominator, that square root of x minus 3, well, I don't want that to be equal to 3. Because if this was 3, the denominator would be 0, and that would be bad. Okay, let's solve this. Let's square both sides. So I'll get x minus 3. If I square the other side, I'll get 9. X minus 3 should not be 9. And moving the 3 over, this is saying x is not going to be equal to 12. And we could check it. If you plug 12 into the denominator, it makes the denominator be 0. Okay, so x better not be 12. Okay, so now I got two even roots. One of them has got x minus 3 inside it. So x minus 3 better be greater than or equal to 0. We handled this one in the previous problem. That just meant x was greater than or equal to 3. And then there's another even root on the top. So that means x minus 10, what's inside of it, better be greater than or equal to 0. And this we handled as well before. Just move the 10 over to get x is greater than or equal to 10. Okay. So now let's see if we can start to put these together. So I need all of these restrictions to happen. So I need this first one to happen, and I need the second one to happen, and I need this third one to happen. That means we're going to have an intersection going on. So let's first put the first two restrictions together. Let's combine them. Okay, so that'll give me a number line. So this is saying that x better not be 12. So 12 is definitely going to be open. X better not be 12. And x needs to be greater than or equal to 3. So x needs to be greater than or equal to 3, but x cannot be equal to 12. So I'll put 3 on the number line. So it includes a 3 because of the equal sign. And everything bigger than it is fine except for 12. X cannot be equal to 12. So this is the number line for just the first two restrictions. Now let's put in the third restriction. Let's just draw a number line for that thing by itself. So 10 is in between 3 and 12. And because the equal sign, I shade in 10. And then I would shade in everything bigger than 10. Okay, so now these two number lines, I gotta combine them with that and statement. And means I gotta do an intersection of these two things. So intersection, intersect, here's my symbol for intersection. And when I do that intersection, let me actually move this a little bit to the side, just so it's lined up with the other number lines. What will I get? So the intersection, I shade in just the values that were shaded in both number lines. The first number that's shaded in both is 10. So I shade it in. And then everything up until 12 is shaded in both, but 12 itself is not shaded in both. 12 is only shaded in the bottom one, it's not shaded in the top one. So I don't shade in 12 in the intersection. And then everything to the right of 12 is shaded in both. Okay, so I've made that intersection. In interval notation, this would be bracket at 10 up until 12 parentheses, union parentheses at 12 to infinity. All right, and that is this domain in interval notation.